This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay, so just to get you oriented, I think you have this in your syllabus. You probably want to keep it out and look at it as I do some of the, probably the last bit of math you'll see in this class. So what's going on here is we know that with energy transfer, energy gets transferred from regions of high temperature to low temperature, and in heat exchangers, there's generally a wall that separates two fluids, wall shown here in pink, across which energy can transfer without actually mixing the two fluids. And the analogy in mass transfer, where the mass flow, say in grams per second, from fluid 2 to fluid 1 happens if the little pink line separating these two fluids actually prevents the fluids from mixing but allows molecules to pass through the membrane, going from a high concentration to a low concentration. And both of these systems are quite analogous in the way they're described mathematically. So what's on what's on the screen here is a situation where there is nothing separating the fluids. So this can be if two fluids were immiscible in one another. You wouldn't need something to separate them because they don't mix. Or in this case, if you have a liquid down here on the bottom and an interface between the liquid and a gas above it. And where we're going with this is this liquid could be a lagoon or a pond of toxic waste. And some of the toxic molecules are exchanging from the liquid into the air and then being blown to places where people might breathe it, as might have happened at a hazardous waste site, which I'll talk about next time. So we need to figure out how to analyze a situation. The problem is the following. You have toxic molecules or molecules in the liquid. They're transferring into the gas. Now, it can go the other way. You can actually have materials in the gas that transfer in the liquid depending on which way the concentration difference is. If the concentration is higher in the gas than the molecules than in the liquid, it will transfer into the liquid. If the concentration in the liquid is higher than in the gas, the reverse will occur. Now, the way that this is modeled, and the way we'll model it, is the following. We'll assume that the liquid and the gas, for the most part, is really well mixed. And it's only near the interface where the resistances to mass transport occur. And that's where the gradients in concentration will be. So if it's well mixed, it's pretty much a uniform concentration. We'll call it C liquid here. And then when you get to this little thin film, in actuality, these can be just millimeters thick, where most of the concentration gradient is taken up. So the concentration in this case is high at the interface and low in the liquid. It's higher in the gas phase, lower at the interface. So in this particular example, the material is being transferred from the gas into the liquid. So let's start out here in the gas phase at a concentration Cg. It drops through this little, it's kind of an imaginary layer where we say all the resistance is, it's where the gradient is, to some concentration of the material in the gas phase, and then there's a jump. You see, one of the differences here, if this was temperature, it would have to be continuous, because temperature doesn't jump. The temperature is continuous. But it can be that with mass, the concentration actually in the liquid side is different than on the gas side, right on the other side of the interface. In this case, it jumps up, and then it drops again down to C liquid. So there's 4 concentrations that are important. It's the well-mixed gas concentration, the well-mixed liquid concentration, the concentration of this same material right at the interface but on the gas side, and the concentration of the same material in the liquid phase but right on the liquid side. And there's this jump. Now, why would there be a jump? Well, there'd be a jump in cases where you have molecules that selectively have an affinity to be in the liquid but don't want to be in the gas phase because of their chemical nature. Or there's some that really prefer to be in the gas phase and not in the liquid phase. And because of that, you get what's called a partition coefficient. That is, it partitions across that interface in such a way as you actually have a difference in concentration in the two phases right at the interface. You get a discontinuity. You cannot have that in temperature. Temperature will be continuous. That's the only difference, really, between mass transfer and heat transfer. And we'll actually focus on this jump. If you had a material, if this was water, and it was really very water soluble, and it didn't care whether it was in the air or in the gas phase, then actually what would happen is CSG would approach CSL and might actually even be the same, if in fact there was no particular partition toward one phase or the other. So let's write down the equations that we've seen before. In heat transfer, we had for conduction, if you recall, Fourier's law, which said that the driving force was a temperature gradient, which drove an energy flow per unit area modulated by the thermal conductivity. This was for conduction. And Q is energy per unit time. Temperature is temperature, X is distance. Now, when we integrated this across a material, say a slab through which conduction was occurring, we got the following equation, that Q over A is equal to K times the temperature difference across the slab, if you will, divided by the thickness of the slab. And for convection, we came up with a similar looking kind of equation where H is called the what? It's a heat transfer coefficient. Has the same units as K over L, as you can see from the equation. And if we took a situation where you had heat transfer through a material of thermal conductivity K, and you had a delta T across this material, you could assign, by looking up in Perry's, a heat transfer coefficient on the fluid 2 side and one on the fluid 1 side. Those heat transfer coefficients would be a function of the kinds of fluids, how fast the fluids are moving, their physical properties and so forth, but you can look them up. And we found out that if you combine these and you want to get an idea of what the heat transfer is through that integrated system of fluid, material, and fluid, Q over A was equal to big U times delta T. And big U was the overall heat transfer coefficient, which was the sum, if you recall, of the reciprocal resistances of resistances to heat transfer on the fluid 1 side, the fluid 2 side, and the material. And if you recall, and I'll write it over here, 1 over big U is equal to 1 over the heat transfer coefficient on the 1 side, the thickness of the material through which the energy is flowing divided by the thermal conductivity, plus the heat transfer coefficient on the other side. And so you can see that 1 over U is a resistance. So these are sums of resistances. And we can look this stuff up in textbooks and we can solve these kinds of problems. Now in the mass transfer, if I were to do the exact same thing, I'd get N, which would be like grams per second, divided by the area, is equal to minus D times dC dx. Now D is the diffusion coefficient. It's like the thermal conductivity. It has units of length squared per time. C is the concentration, and X is distance. And this is for diffusion of material from one point to another. And diffusion occurs through a medium. And the diffusion coefficient depends on two things. It depends on the molecule that's diffusing and on the medium through which it's diffusing. You look that up in Perry's. And you can integrate this as we did, so that for diffusion, just like in heat transfer, you'll get N over A. And what's another word for N over A? What is that? It's a flow, grams per second per area of flux. A flux. You should have brought some more beer with you. Why? For convection, N over A is equal to, I'll put a hat on here, a mass transfer coefficient times a concentration difference. The mass transfer coefficient has units of d over L, which means it's length per time. And if I have a situation, as we did in the artificial kidney, where I have a fluid on one side of a pink membrane and a fluid on the other side, this was dialysate and blood, I would have a mass transfer coefficient on the fluid one side. I would have a diffusion coefficient and a thickness of the molecules through the pink membrane. I would have a mass transfer coefficient on the fluid 2 side, which would depend upon the kind of fluid, the molecule that's actually moving through the fluid, and the fluid properties. I can get an overall expression just like we have over here. If I take that combined system, I can get an overall mass transfer coefficient, a driving force of a concentration difference between fluid 1 and fluid 2, and K, 1 over big K, is simply going to be equal to 1 over the mass transfer coefficient on fluid 1 side plus 1 over the mass transfer coefficient on the fluid 2 side. So they're actually identical in terms of the mathematical formalism. What's that?
Isn't it U equal that, not 1 over? Because 1 over U is...
Yeah, is it?
Yeah.
Yeah. Sorry. Is that right? Does that correspond to things? Let's see, let's check it out. U has the same units as this. So if I have 1 over that, I have the inverse units, and if I invert them again, I'll get back the units of U. So thanks. Yeah, sorry. Little neuronal loss. Okay. So that's where we left off. Now let's apply this concept here.
How does convection work with mass transfer?
If you have, let's say, the dialysate fluid in the artificial kidney, and you have urea coming across here. If I mix this up really well, and I get the urea away from this membrane and get it out into the bulk, that will enhance the transfer of urea, as opposed to having, let's say this fluid wasn't moving at all, then the urea would build up here and it would cause the flux to decline. So think of it about mixing. And mixing on this side will establish the sizes of these mass transfer coefficients. And of course, remember, you can calculate where the resistance is. If you know the values of each of these terms, you'll know where the resistance is to the transfer of either energy or mass. Could be on the fluid 1 side, could be on the fluid 2 side, or it could be actually what it's going through, the separator between the two fluids. So I'm going to use this terminology now, so you'll have it in front of you, the CGs, the CSGs, and so forth. So you might keep that in mind, because I'm going to put the screen up. Somehow. Look for a switch. Yeah. And so do a little formalism. This gets a tiny bit tedious, so bear with me. And I'll use the same So first of all, we're going to be at steady state. Don't copy that down. That actually happened one year. There was a board. I didn't see there was all a bunch of quantum mechanics on it. And then this final gets turned in, and this kid wrote all this stuff down. I looked, my God, it looks like Einstein. I realized he had no idea what was going on in this class. He just copied that down on his final, hoping, because it looked good, that he'd get some credit. He's now selling newspapers. So at steady state, we'll have the flux in that system that I just showed you, the sort of the liquid water system. We'll have the mass transfer coefficient on the gas side times Cg minus CSg. And at steady state, that has to equal the mass, of course, that's going into the liquid, CSL minus Cl. And in this case, for n less than 0, for release in the meaning or emission, so this is the system where we have a liquid and a gas. And in this particular case, which I had drawn, Cg was bigger than CSg. And so n is positive, and so the material's going from the gas into the liquid. Obviously, if these signs change, then the material will be leaving the liquid and going into the gas. And of course, I have to equate these, because this is basically the mass that's leaving the gas phase, entering the liquid phase, or mass entering the gas phase is leaving the liquid phase. All right, so let me take this and rearrange it. I'm going to work with these two equations here. So we have Cg, Kg hat from the first one, minus CSg. So actually, try to pay attention to this, because it's easy for me to sort of zone out and make a mistake here. Minus KL times CL. All right, so I just multiplied through with the mass transfer coefficients. And then I'm going to, I won't do a dirty trick, because I could actually just like start erasing, and you can't do that in your notes, so I'll write the next line down, which is Cg Kg hat minus CSg Kg. The first two terms are the same. I'm going to bring over this KL term, CSL, on the other side of the equation. All right, so I just brought that over on the other side of the equation. Already, let's make sure we've got one there. Yeah, okay, good. And now I'm going to add, let's see if we can fit this. So your paper's probably, all right. So I'm going to rewrite this, but I'm going to add, I'm going to multiply every term in this equation now. And you can do this in your notes, say he multiplied, by a thing called h prime, okay? So I'm just going to multiply every term by something called h prime, and let me define it for you. Okay, so h prime is equal to CSG over CSL. It's the ratio of the interfacial concentrations in the gas phase and in the liquid phase, right at the interface. So I haven't done anything. I can do that. Now, next thing I'm going to do is I'm going to add to both sides of this equation Cg times KL. So let's write that down, Cg, Kg, and then we got minus h prime, CSG, Kg hat minus h prime, KL, CSL minus KL CL H prime plus C, this is the term I added. So all I did was add this and this, if we got it right, to either side of the equation. All right, so now I can gather some terms here and do some factoring. So I get CG minus CSG times KL plus H prime KG equals to KL CG minus H prime KL CL. So we can kind of multiply that out, make sure we recover all the terms of that top equation. All right, so this is this side. These four terms combined there. Okay, so I can solve for CG minus CSG, which is going to be, just again, rearranging. Or if I just divide through by KL. And now I can go back up to the top equation. Now you see I have an expression for CG minus CSG. And of course, the whole part of this was CSG is not something I can easily measure. That's its interfacial concentration. So I'd like to get it out of the equation. So I can write that N is equal to Kg. Did we forget a minus?
It doesn't work. Yeah.
It doesn't work?
No, because you have
Too many H terms.
and your CS you end up with a CSG KL, which is
Are we talking about this one?
no the one above it.
Okay.
Yeah.
CG minus CSG, KL plus H prime equals CG minus H prime KL CL. Okay. So, aha. You see what happened here, though? See this term right here? I use this. H times CSL is a CSG. That's good, though. So that's where the CSG came from. Any other complaints? No, that's good. You're staying with, and we're almost done, which is really the best news of all. So we get Kg is Cg minus CSG. Okay, so it's Kg times this. And so I'll write it down, Cg minus CSG. So we substitute this in here, multiply through this by Kg, and lo and behold, we get Cg minus H prime Cl divided by 1 over Kg plus H prime over Kl. And I just took the Kg underneath. Okay. Or by just multiplying by 1 over, I can also rewrite this by just multiplying top and bottom by 1 over H prime. So those are equivalent. And this is the, so n is equal to this. And so now what does this start to look like? This looks like n is equal to, now this n, by the way, if we look at it, why don't you take that n, so you don't get it confused with this one, and put a little bar over it, because this is a flux, so that's really little n over a. So we'll call that a flux. And so we'll call this a flux. So we have a flux, n, or n over a, is equal to a driving force divided by what? The sum of these resistances. So this thing, these things look like what? Overall mass transfer coefficients. So we have n is equal to, I'll call it big Kg, that's capital Kg, times Cg minus H prime Cl, which is equal to, or big K, well, I'll call big KL, which is Cg over H prime minus Cl. These are equivalent expressions. And you can see by comparing the two expressions, you can see that 1 over big Kg is equal to H prime over big KL, or H prime is equal to big KL over big Kg, but we've also defined it as CSG over CSL, back up here at the top. Now you might say, well, this all looks like smoke and mirrors. You didn't really get rid of CSG, it's because it's buried in the H prime. And so what have you accomplished with all this stuff to get to an equation that looks a lot like our friend here, where we have these overall, we call this the overall gas phase mass transfer coefficient over the overall liquid phase mass transfer coefficient. Well, the reason is because if we go to the ideal gas law, and most of the time these solutes that are coming out of toxic waste pits are in very low concentration, so they're kind of like ideal solutions. At the interface, if I rearrange this, at the interface between the gas and the liquid, on the gas side, if we consider these molecules to be ideal, then the number of moles per unit volume is equal to the pressure, which is the vapor pressure that's exerted by these molecules out of the liquid phase, divided by RT. That's nothing more, if you look at this, grams per unit volume or moles per unit volume, as a concentration. So that formally is, in fact, what CSG is. And CSL, if you think about it a minute, that is the concentration right at the interface on the liquid side is really nothing more than the solubility of the molecule in the liquid phase. It's how much it can be put there in the liquid phase. And so H prime,
What are the units of K?
this K?
Yeah.
Okay. Should be the units of this K, which should be the units of this K. The units of this K should be the units of D over L. Centimeters squared per second divided by L is centimeters per second. So it's length per time. All right, so if we take a look at what we have over here, we see that H prime is simply the vapor pressure, which is something I can look up in a table of the molecule, divided by its solubility times RT. And sometimes this is written as H over RT. Where H, therefore, this H is just equal to the vapor pressure divided by the solubility. The difference is that H prime, what are the units of H prime? Unitless. So H is dimensional. It's a pressure divided by a solubility, like grams per cc. H prime is dimensionless. You'll see this in textbooks, so I give it to you because you'll see them both. RT at 20 degrees centigrade, R is the gas constant. At 20 degrees centigrade, just to give you, is 2.4 times 10 to the minus 2 atmosphere meter cube per mole. You can look that up in Perry's if you don't believe me. And the vapor pressure can be given in millimeters of mercury or atmospheres, pounds per square inch, and so forth. So we now have an expression for H prime that we can actually look up in a book by knowing vapor pressures and solubilities, and that takes care of us not having to know the actual concentrations at the interface. So now what I want to do is, if you look at this equation, what this allows us to do, just so you know why this is important, is if I can get values of Kg somehow, where do you think I'm going to get these values? It's the only thing I've ever asked you. Perry's, or something like Perry's. So the flux, either into my pond or out of my pond, if I know Kg or Kl, one or the other, if I can measure the gas phase concentration, which I can do, I can go above the pond, I can measure the gas phase concentration in the pond, above the pond. I can measure the concentration of the stuff in the pond. If I know H prime, which I can look up in a book, I can calculate the flux. I can calculate how much is going to come out. Now, let me give you an example. We'll work an example because you need to know where you can find this stuff. And this turns out to be pretty cool because I can tell you that when I went into the courtroom and I had to explain this to a jury, that you could actually calculate how much stuff came out of these ponds years after the fact, I was just simply using these equations. So there are books, and a particularly good book is, there's a book by Lyman, which is on your reserve list, and it has this plot in it, and this is a plot of vapor pressure versus solubility of a whole bunch of different molecules. And if you look at these molecules, chlorobenzene, toluene, chlorobutane, 1,2-dichloroethylene, hexachloroethane, all these chlorinated or brominated or halogenated molecules are some of the toughest molecules to get out of groundwater. They contaminate groundwater, and you need to know the rate at which they're going to be transferring from one phase to another so you can think about how to clean up groundwater. Now, do you see these lines here? 10 to the minus 7th, 10 to the minus 6, 10 to the minus 5, 10 to the minus 4. These are values of H, and H has a name. It's called the Henry's law constant. Now, this is H, so it's the dimensional H in these units, atmosphere cubic meters per mole, going from 100 to 1 to 10 to 1, 0.1, 0.02, and so forth. And you'll see all these chlorinated molecules tend to aggregate between Henry's law constants of 10 to the minus 1, and with phenol, get up here about 10 to the minus 6, about 5 orders of magnitude of Henry's law constant variation. These have been plotted by knowing the vapor pressure and by knowing the solubility in water of these various molecules, including N-octane, which is equivalent to gasoline sorts. Now, another way to look at the same information is in tabular form. But before I do, I want to just give you a hint about what these Henry law constants mean physically. There we go. Oh, is that better? All right. I could make you stand on your heads, I guess. So here's H, the Henry's law constant that we got over here in our analysis, going from 10 to the minus 7th to 10 to the minus 2. So low values of the Henry's law constant, high values of the Henry's law constant. Now, as we're going to find out, is that materials that have very low Henry's law constants are essentially non-volatile. They basically have a very hard time vaporizing out of the liquid phase, getting out of the liquid phase. Whereas the higher numbers are the more volatile molecules. That's one thing to remember, and you'll see this now on a table, and you'll see why. Because remember, that's just this interfacial concentration difference. And so here's a very sort of interesting table from Lyman. And you'll see what he's done here is he's giving you a list of these very same chemicals that were plotted, their molecular weight, their solubility in 2 different units in water, their vapor pressure in millimeters of mercury in atmospheres at 20 degrees centigrade, the Henry's law constant, both dimensional and non-dimensional, and the only thing that relates these two is RT. And then the phase exchange coefficients in length per hour for KL and KG. This is little KL and this is little KG that we have in our analysis. And this is big KL. We could have also put big KG there because you see big KL and big KG are related by simply H prime. So he's only listed one of them here in centimeters per hour. Now, the interesting thing to note as you go down with these chemicals, the way they've been arranged, is they've been arranged in such a way that the gas phase, look at the gas phase value here. It's pretty large, 1100, 1500, 11, 2000 down to 1400. The liquid phase number is 16, 12, 14. Now, what does this all mean? In fact, there's another, and I'll give you an example to show you what it means, but take a look at this continuation of the table. You'll see that the liquid phase coefficients are ordered such that they're kind of increasing here, and these gas phase coefficients all seem to be roughly about the same. The overall coefficient, however, if you look at it, tracks more the value of the liquid phase coefficient. See, they're pretty close all the way down. So what is this telling us? And the only way I can tell you what it's telling us is let's just take some examples. So I'm going to turn the light back on. You have this table in your notes because I'm going to ask you some questions about some of the values. So let's pretend you're an engineer now. You've been asked to comment on the transfer of dieldrin. Now, dieldrin's an insecticide. And the consulting job that you have, that you're charging $450 an hour for, plus travel, and lodging and expenses and food and entertainment. Never forget the entertainment, by the way, because they don't expect you to be just a total nerd. So, dieldrin. So this is an insecticide, and you have dieldrin in this water, and it's going to escape into the gas. And remember on heat transfer where we always had one of these controlling resistances was either on one of the liquid sides or it was the conducting medium itself. The question is, what's controlling the resistance of dieldrin to get from the liquid phase to the gas phase? Well, it turns out you can now calculate it by calculating the overall mass transfer coefficient, 1 over big KL. And now 1 over big KL is equal to what? It's 1 over tiny, you got to tell me because I erased it, tiny KL plus what's the other term? I wrote this down. RT over H kg, okay? So I want you to look up in the table, what is KL for dieldrin? Little KL. Little KL. 12. Now, what did I say RT was? I said it was 2.4 times 10 to the minus 2. What is H for dieldrin? 2 times 10 to the what?
Minus 7.
Minus 7. And what is Kg for dieldrin? 990. So this turns out to be 0.0833 plus 121.2. Now, these are sums of what? Resistances. So where is the resistance to transfer of dieldrin from a liquid phase to a gas phase? Is it coming from the liquid or is it coming from the gas? The gas. So about 99.9% of the resistance is from the gas phase. So what does that mean physically? It means the little dieldrin molecules distribute throughout the liquid phase, and they get to that interface, and now they want to pop out into the gas phase. But what do they see when they try to pop out? This huge resistance. They don't want to be in the gas phase. So when we say the resistance is in the gas phase, it's tantamount to saying that there's no resistance to transport in the liquid phase, and for all intents and purposes, the dieldrin is distributed evenly throughout. There's very little gradient on the liquid phase side. It all exists on the gas phase side. That's where all the resistance is.
To latent heat?
To what?
To latent heat, the energy required in order to change phases?
It actually has more to do with the affinity of the molecule for the phase in which it sits. So if it would prefer to be surrounded by water than to be in air as a volatile compound, in this case it wants to sit in the water. So you think, because it's more the chemistry of the molecule than it is anything about its energetics. It would just prefer to sit in the water. And so the concentrations of this stuff above the gas phase would be very little. So in fact, dieldrin, as a gas phase contaminant that you would breathe in, it's not very serious. In fact, what happens, and since many of these chemicals are dumped in unlined pits, which have soil, molecules like dieldrin happen to be have a very high affinity for soil and soil particles. And so they'll actually get sucked out of the ponds onto the soil that the ponds are made from until all the sites are saturated. This makes for a big problem when you drain these ponds and you clean it up, then you're left with all this soil. It's very highly saturated with these chemicals. That usually has to be dug up, trucked away, or incinerated. Now let's do one other example so you can see the difference. Let's see, what did I do here? I did trichloroethylene. So let's do trichloroethylene and see how that molecule is different. So what is little kl for trichloroethylene? 21. Not that much different than for the dieldrin. Plus, we get 2.4 times 10 to the minus 2. What is H for TCE? Huh?
1 times 10 to the negative 2.
10 to the minus 2. And what is little kg for how much? 1700. So when I calculate this out, I get 0.0476 plus 0.0014. Where's the resistance to transport of TCE dissolved in our water and getting out into the atmosphere? Here's the liquid phase resistance. Here's the gas phase resistance. Where is it? It's in the liquid phase. And in fact, this is about 97%. So here you have two different molecules that behave very, very differently in our system. The TCE, this is the picture you have TCE. You're a TCE molecule. You're swimming around in there, and you get to this interface, and what happens? Boom! Man, you're just out of there. There's no resistance. It's wonderful. And so where the resistance is in the liquid phase, all the other little TCE molecules crawling around trying to get up to the interface. Whereas with dieldrin, they're everywhere. They're all sitting at the interface, and one pops out and one pops out. So it's kind of an inverted way of thinking about it. And yet, dieldrin and TCE are quite different molecules, but their resistances and their gas phase resistances and their liquid phase resistances are quite different. So if you look at what KL turns out to be, if I actually calculate KL, and that happens to be in the table, if you use our numbers, it's 8.2 times 10 to the minus 3. This is the overall. And what does it say in the table for it? Pretty close to that, I would guess. For big KL, the column on the right. 8 something? 8.8. Yeah, okay. That's close enough for engineering. And KL for TCE is what? How much? 20.4. So this is the last thing I wanted to show you. Look, when you've got liquid phase resistance governing it, the value that the overall liquid phase mass transfer coefficient takes is that of little KL, because that's the driver. This term doesn't matter. So big KL approaches little KL as the resistance to the liquid phase governs. And the vice versa. If I had calculated kg for here, kg would be something like, big kg would be something close to 1,000. So one of the ways that if you look at that table, you can look at those compounds, and you can look at that table and see all the compounds where little KL is almost the same size as big KL. They're all liquid phase controlled in their release. And how many of those look like that in that table? How many of those chlorinated compounds seem to have little KL and big KL pretty darn close? Most of them. So this is going to be an important clue when we solve the Stringfellow problem next Wednesday, because Monday you have holiday unless you want to have class. That's okay. Okay, we won't do that. Theo said that's a bad idea. So we're going to now take this, and I'm going to take you through a litigation and a story of how massive consulting was done with this. You could retire based on what you learned here today, if you use this properly. You had a question?
The Aldrin, though, the K doesn't match up with the one with the more resistance against resistance.
What doesn't match up now?
So if there's something like the Aldrin where the most of the resistance is in the gas phase, should the big K match up with the gas phase?
The big Kg should.
Oh.
So you're going to have to take, you have KL, so you're going to have to take, solve this, invert it. If you divide it by H prime, I bet you would get something that looks like this Kg right here. That's when little kg and big Kg. Okay? Yeah?
Sorry to track back, but where did we get the equation 1 by big KL equals 1 by small KL plus R2?
Which one?
The one that we used to calculate the big KL. Just one.
The one right there.
Oh, yeah.
Yeah.
1 over K equals 1 over L.
Where did this come from?
One over one dial.
This one?
Yeah, it's the same thing. But where did we derive it from?
Where did I get this from?
It's the resistance.
It came to me in a bad dream. I think it was the end of the derivation, right? The end of the derivation on the previous. Can you show her where that came from? Yeah. Did you see that? So it came out of that derivation. All right. Have a great weekend. Have a nice Memorial Day. And we're going to solve a big environmental problem on next Wednesday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.